I want to talk today about very basic NMR theory and how the NMR works and how you generate an NMR signal. And we're going to start with some really fundamental things about the structure of the atoms. First, the nucleus contains protons and neutrons. That's something we all learn in our first chemistry class. Next, the protons in the nucleus are spinning. We're not going to worry about what the neutrons are doing, but the protons are spinning. Anytime you have a spinning positive charge, you generate a magnetic field. So the spinning proton, spinning positive charges, generates like a little bar magnet, and you get a magnetic field generated by these spinning protons. In the absence of an external magnetic field, the nuclei's magnetic field is oriented randomly. So here is a depiction of that. I have my different nuclei, and the arrows indicate their magnetic field directions. Some are going up, some are going down, some are going to the side, some are going diagonal. In the absence of an external field, the orientation of these magnetic fields is random. However, in the presence of a strong external magnetic field, the magnetic field of the nucleus is not random. It must be aligned either in the same direction of this magnetic field or the opposite direction. When we say external magnet, that's the NMR. The NMR contains a very powerful magnet, and the nuclei in our sample must align their spins either in the same direction or the opposite direction of the magnet of the NMR. So here's sort of a diagram of that. This B0, B represents the magnetic field of the NMR, and it's going in this upward direction. And the protons that we're studying in the nucleus are generating their own magnetic fields, and they can either go in the same direction as the NMR or the opposite direction of the NMR's magnetic. So this one is going in the same direction as my magnet, and this one's going in the opposite direction of my magnet. And again, those are the only two possible choices. There's actually another way to visualize this in a different type of diagram. These over here are my random magnetic fields from my protons in my nuclei, not in the presence of a magnet. I put them in the presence of a magnet, and they orientate their spins in the same direction as the magnet from my NMR or the opposite direction of the magnet from my NMR. And I want you to notice a couple things here. These are really important things. The first thing I want you to notice is that when the spin is oriented in the same direction as the magnet from the NMR, it's lower in energy. And when it's oriented in the opposite direction of the magnet from the NMR, it's higher in energy. And I'll squeeze that in over here as number 6. Spins, and when I say spins, I mean spins that generate the magnetic field oriented with the NMR magnet are lower in energy. Spins opposite are higher in energy. There's another thing I want you to notice also. We can have NMRs with different magnetic strengths. We can have a weak magnet or we can have a strong magnet. And what I want you to notice is as the strength of the NMR's magnet gets larger, the difference in energy from the high energy spin state and the low energy spin state gets greater. And again, I'll squeeze that in over here. As NMR magnet strength increases, energy difference increases. The next thing to consider is that if we shine light on our sample, the lower energy spin will flip to the higher energy spin if we hit it with the right energy of light, the light that corresponds to this delta energy gap. And we can look at that in sort of another diagram. So we can see in this diagram, we have our spin, nuclear spin in the low energy state. We shine light on it. If the light happens to be of the energy that corresponds to the gap between the low energy and the high energy state, the nucleus will absorb it. Its spin will flip over to the high energy state. So the thing that makes the NMR really useful in analyzing our samples is this next thing. Spinning electrons also generate a magnetic field. And this magnetic field is opposite of the magnetic field of our NMR. So it weakens the field of the NMR magnet in the area close to those electrons. So the reason that this is really important and really useful is if we have a nucleus that's near low electron density, the electrons are not generating much of a magnetic field, so they're not weakening our magnetic field from our NMR very much. So the magnetic field in that region is pretty strong. And since it's pretty strong, the energy gap between the two spin states is pretty large, and it takes higher energy or shorter wavelength light to cause the transition to happen. On the other hand, if the nucleus is in a region near high electron density, the relative magnetic field is weaker. The energy gap is less, and it takes lower energy or longer wavelength light to be absorbed. So by measuring how much energy or the wavelength of light that it takes to cause this transition to happen, we can tell about the environment that our nucleus is in. We can tell what it's bonded to. This makes NMR really, really useful. And I want to look at an example of that. First, we need to talk about a couple of terms. Specifically, we have to talk about shielding. Shielding talks about the electron density near a nucleus. The more electron density near the nucleus, the more the shielding. So this hydrogen that's on the oxygen is less shielded, or sometimes we say deshielded, because the oxygen is electronegative. It pulls the electrons towards it. So the hydrogen is in a less shielded or less electron dense environment. On the other hand, carbon is not very much more electronegative than hydrogens. It doesn't really pull electrons away from them at all. So these hydrogens on the carbon are more shielded. They're in a higher electron density environment. So if we look at an NMR spectrum of this molecule, we see that the hydrogen on the oxygen is in the presence of a stronger magnetic field, so it shows up in this region. It takes higher energy light to cause the transition, whereas these hydrogens on the carbon are exposed to a lower magnetic field. It takes less energy to cause the spin transition, and they show up here. They show up in different places because of the electron density around them. And this is what we use in NMR. Our knowledge of what types of functional groups, what types of environments cause the spin flip to happen in different regions. And that's how we're going to analyze our samples in NMR.